So for part one of the dataset, I'll be importing um, my dataset and also various libraries such as OS, which will be used for the file path. Next up will be pandas to read the dataset and check for missing values or access a specific column inside the dataset. I will also be importing matplotlib for data visualization purposes. I'll also be importing Seaborn to help me make the heat map. I'll also be importing NumPy for evaluating the model, and I'll also be implementing sklearn, more specifically train test splits to split the dataset into training and test sets. I'll also be importing linear regression, the decision tree regressor, the mean squared error, and the R2 score for model evaluation. And I will be importing the cross validation score, which will be used for the optional enhancement. Okay, now let's run this code. Okay, yeah, so as you can see, we have the contents from the datasets. Well, like not all of them, but some of them. Um, and next up, I'll, I've also I've also put print data is null to check for missing values in each column, and it prints the amount of missing values in each column. So, so as you can see here. For the next step of the coursework, I have to do a bit of data visualization, and I'll be using a heat map for that purpose. So the first thing we do is only select numerical columns from the dataset. Next up, we compute the correlation matrix to help find patterns and relationships within the data. Uh, and then once that's done, we create the heat map. Let's try run this code. And yeah, here is the heat map with the data from the dataset. So according to the heat map, we can see the values with the strongest correlation with the target variable have a value of 1, while the values with the weakest correlation have a value of minus 0.63, 62, and 61, and 63 up here. Part 3 is the data prep section where we prepare our data to be used by the machine learning model. So first we set a variable called x, which uses all the columns in the dataset except y. And then we set a variable called y, which will be the variable we want to predict, and it only uses the y column from the dataset. So we then split the dataset into a training set and a test set to allow us to evaluate model performance on unseen data. So I have set the training data size to 80% and the test set size to 20%. Now I'm going to run this code, and as you can see, it prints the X training set, and it also signifies that the dataset has been split up into a training set and a test set. Part 4 is where we build the model and it makes predictions. So we will be using a variable called linreg, which contains the linear regression function to create the linear regression model. And we will also be using a variable called treereg, which will contain the decision tree regress function to create the decision tree. So for the optional enhancement, I will be doing k-fold cross-validation to split the dataset into 5 parts. Um, so 4 parts will be used for training and 1 part will be used for testing. So in simple terms, the model is trained 5 times and we get 5 scores. So the results will have the root squared score, the average root squared score to show the average performance, and the number of folds. This will be done for both the linear regression and decision tree. So we use linreg.fit to train the model using the x and y training sets, and we use treereg.fit to train the model using the x and y training sets. After that, we generate predictions on the test set and print out the linear regression predictions, and we do the same thing for the decision tree predictions. And let's try run this code. Yeah, so as you can see, we have the root squared, average root squared, number of folds, and the decision tree cross-validation. We also have the linear regression predictions and the decision tree predictions. Part 5 is where we evaluate the model's performance. We will be using mean squared error, root mean squared error, and root squared to evaluate both models. And once that's done, we will print the results. Okay, as you can see, here are the results for linear regression with a mean squared error of 9.3, a root mean squared error of 3.05, a root squared of 0.84. For the decision tree, we have a mean squared error of 17.9, a root mean squared error of 4.2, and a root squared of 0.69. For the linear regression results, the mean squared error is 9.3. It's pretty low, which is good. So the root mean squared error shows my predictions are about 3 units off from the actual target value, and the root squared shows the linear regression model explains 84% of the variations in the target variable. Now, for the decision tree, the mean squared error is much higher than linear regression, which means it's uh, weaker than linear regression. The root mean squared error um, are 4 units away from the actual values, um, and the roots squared score is pretty decent as it explains 70% of the variations. But overall, I would say linear regression is more accurate, but this could be because the decision tree's depth is too short. One of the optional enhancements I did is uh, visualizing the results of both the um, decision tree and the linear regression models using a scatter plot in order to make the results much more easier to be understood. Okay, as you can see, here is the scatter plot with the actual versus predicted values. So blue stands for linear regression and orange stands for decision tree. So as we can see from this graph, so the linear regression dots stay close to the red line, meaning that linear regression captures predictions well, but sometimes it can overestimate or underestimate some points. The decision tree, on the other hand, captures some patterns, but it's not really that accurate compared to a linear regression due to some dots being spread out far away. Okay, so that brings us to the very end of my coursework. Um, as you can see, I have some references here. These I use these references to help create my code along with the materials from the lab sessions.